Okay, here is our video for applications of torque. We've got a couple of class problems here. At the time of recording this video, there are 4 pages for these class problems. 2 of those pages are just way too difficult. Um, so don't worry about those two. We will only be working with 2 of these pages today. At the time of recording, this is page 19 and 21 are the ones that we will worry about. Um, so just cross off the others. It doesn't matter. I mean, feel free to try them if you want, but they are very difficult, which is why we're not working on them. Okay, here we go. So we've got in this first situation, you might recognize what this looks like, right? This is a modified Atwood machine. We talked about these in forces where you have right, you have one block sitting on a table connected by a string over a pulley, another block hanging down. So we've talked about these before as far as just forces goes. But one thing that we always said with forces, oh, excuse me, one thing we've always said with forces was that there was a massless pulley. That was something that was always just so incredibly important with our forces conversation about this all. However, now you get to learn what to do when the pulley actually has mass. We had to wait until this point in the year because, right, when the pulley is, or what, sorry, when these blocks are moving, the pulley is rotating. So, right, the entire pulley is rotating. So, we couldn't deal with that earlier. You didn't know how to deal with rotating things before now. So, now instead of a massless pulley, we are going to have a pulley that actually has a mass. But remember, mass is analogous to I, or rotational inertia. Okay. So as we go through this problem, we'll show you how to deal with all that. Okay. 2 identical blocks, masses 2.0 kilograms, so 2 kilograms for both masses, 2 kilograms. They're connected by a massless string. Sorry, that circle got in the way. 2.0 kilograms. They're connected by a massless string. Oh, okay. So the string still has a mass. Still has no mass. The string still has no mass. That's helpful. They connect over a pulley of radius r is zero point 0.2 meters. So r is 0.2 meters with a rotational inertia I 0.03 0.03 kilogram meter squared. Okay. This is kind of how AP will like to give you these rotational inertias. They'll just give you the number of kilogram meter squared typically. It's not often that they will have you find it. Sometimes they do, but typically they just will give it to you. All right, the string does not slip over the pulley, so it accelerates with the edge of the pulley. The string accelerates with the edge of the pulley. What does that tell us? Well, that tells us that the velocity at the edge of the pulley is going to be equal to the velocity of the string and the blocks, which is the same as omega r. Okay, so we know that the velocity of the pulley is the same as the velocity of the blocks, which equals omega r. That may or may not come in useful, but that's what that portion tells us. Okay, there is friction between mass 2 and the tabletop, so I'm going to draw that there just to show there is friction as it moves. The other thing I'll draw, force of friction. Okay, the pulley's axis has no friction, so there's no other torques. When the system is released from rest, the pulley turns through an angle of delta theta is negative 10 radians in 1 second. Okay, so in 1 second, it turns through delta theta is, in 1 second, turns through delta theta is negative 10 radians. Remember, negative just means it's clockwise. So that's not, that negative sign is not important, but that tells us how far it goes. Okay. We are looking at part A here. Find the angular acceleration of the pulley. All right, angular acceleration of the pulley. Well, alpha. There's a couple ways that we can solve for alpha. One, I'm just going to write alpha is what we're looking for. One way that we've learned how to solve for alpha, right? We can use this whole sum of the torques equals I alpha equals, and then all the torques that apply. Another way that we've learned is right rotational motion equations. Rotational motion equations. Those are really the only ways that we've learned so far that deal with alpha. So we know it's going to be one of those. Well, I would argue that rotational motion equations is probably a little easier than this line of sum of the torques. So let's try that out first. Remember, for rotational motion, we need 3 to solve the fourth. Okay, so alpha, let's see if we have 3. Well, I see 1. One of those happens, right? Time is 1 second. I'll highlight. That's a better way to go. I see 2. It goes through negative 10 radians. And I see from rest 3. Okay, so we know that omega naught 0 radians per second. We know that our displacement delta theta equals 10 radians. Remember, negative 10 and 10 radians, that just means clockwise versus counterclockwise. We see time equals 1 second, and we are looking for alpha. Well, there is an equation for all those. We have delta theta equals omega naught t plus 1/2 alpha t squared. Recommend pause and try to solve this on your own just so you get the practice. Okay, so we got 10 radians is omega is 0, omega naught is 0, so that all goes away. So we get 1/2 times alpha times our time, which is 1 squared. Okay, so we can solve this. 20 equals alpha. Oh, I didn't leave enough room for my units here. All right, 20 and alpha is radians per second squared equals alpha. Okay, so we get 20 radians per second squared is our alpha there. Nice. And so far, this is just rotational motion equations, right? We know that these are the only two things that alpha kind of shows up in, and rotational motion equations are just easier to solve than torques. So we'll just try to solve that first, and if we can, great. If not, we try the torques. All right. Part B, find the acceleration of the two blocks. Well, that means we're looking for A. Well, we know alpha. Do we know the radius? Do we know the radius? Yeah, we do. We do know the radius up here, 0.02 meters. So this tells us, all right, I'll use a different color. We know A equals alpha R. Okay, we know alpha, we know R. So our acceleration, alpha was 20 radians per second squared, and our radius, 0.2 meters. Make sure I have that right. Yep, 0.2 meters. Throw that into your calculator. You should be getting 4 meters per second squared. All right, so there's our acceleration. Remember, this is linear acceleration. I'll throw that all in a box. Linear acceleration of the blocks. All right. If you need to go back and recap, go for it. So far, this has all been a refresher. Nothing new has happened yet. But now it's about to. It is about to have something new. Because to solve this next question, we are going to just take a closer look at the system here. When I have this block, right, this block is pulling, it's being pulled down by gravity. Here, I'll make a better little drawing over here. Okay, table, pulley. Then we have block, string attached to other block over here. Okay, when I have this block, there's a couple forces acting on this block, right? One, force of gravity. Two, force of tension. I think this was block one, was it? Yeah. So we'll call that force of tension one. Over on the other side, all right, couple forces acting here. Always start with gravity. What's keeping it from accelerating to the center of the Earth? The normal force of the table. We also have tension. This is block two. I'll say gravity two, gravity one. And then there is friction. So we have force of friction there. Okay. Here is now something that's different. Something that's different about all this. And I'm actually going to give myself more space here by moving these down. Move those down just a little bit. Connect the rope. What's different is if we zoom in on this pulley right here and just pretend that here, actually don't pretend, I will draw you a better picture. Right here we essentially have tension 1 exerting a torque on the pulley, so I'm going to say torque of tension 1. Up here we have another torque being exerted on the pulley, right? We know it's a torque because 1, it's not at the center. 2, it's makes it rotate. So we have torque of tension 2 is right there as well. And I'll make my pen smaller so we can actually read this all. So we have torque, oh my, undo. We have this torque of tension 1 and torque of tension 2. Tension 2, torque tension 1. And it's at some radius r away, right? But that's just the radius of the wheel. Okay, because what's happening here? What's happening here? This right there, that rope is pulling on. Actually, you know, I'm going to start the other way. This rope right here. What is that rope pulling? That rope is pulling mass 2. Okay. The difference, that rope is just pulling mass 2. The difference now comes in, what is this rope doing? That rope, it's also pulling mass 2. It's pulling the rest of this rope here, but it's also pulling the wheel. So we can't say, actually, we're not allowed to say that the tensions are equal because the second rope up here, the second rope is only pulling mass 2. But this first rope that's connected to block 1 is not just pulling mass 2. Sorry, my cat's trying to get some extra food. It's not just pulling mass 2, it's also pulling the wheel. So this rope pulls mass 2 and the pulley. So it pulls mass 2 and it pulls the pulley. Okay. What does that mean? Well, since this rope is only pulling the mass, but this rope is pulling the mass and the pulley, that tension 1 is not equal to tension 2, so FT1 not equal to FT2. This is weird, right? Because everything that we've been working with, force of tension 1 was equal to force of tension 2, so we just kind of ignored them all. But we can't do that anymore. We cannot do that anymore because of this pulley. When the pulley has mass, that means that the first rope just is pulling the mass that's on the table. The second rope is pulling the mass that's on the table, and it's pulling the wheel. Okay. So that makes for some interesting situations here. So now we're looking at part C where it says find the tension of FT1. Well, that means we can't just use find tension. We can't just say that because this is tension of FT1. So we're looking for this one right here. It is a different tension than the other tension is. All right, FT1 is this, and FT2 is this. They are different numbers. Okay, so to find the tension in FT1, we're going to do a couple things. One, we need to see where does FT1 apply? Okay, so we've got two things here. We know that FT1 exerts this torque of tension 1 on our wheel, but we also know that from the box, we have FT1 is exerted up. Well, which way is going to be easier to solve this all? Is it going to be some of the torques for the wheel, or is it going to be some of the forces for the block? Well, what do we have the acceleration of? Well, we have the angular acceleration of the wheel. Okay, we have the linear acceleration of the blocks. Okay, so we have alpha and we have A. The difference is we don't know what tension 2 is, right? Because this torque caused by tension 2, we don't know tension 2 for the pulley. So we can't use the pulley yet. We can't use that pulley yet because we don't have tension 2. So we have to use some of the forces for block 1. All right, let's try it out. So, right, we're looking at block 1, some of the forces, and right, this is vertical, but it really is along the string because that's what we look at in Atwood's machines. Right, so equals MA equals, and then positive forces. But again, right, this is, we'll take positive to be the direction of motion. So I'm going to say gravity. Gravity is positive, gravity is down. So Fg, and then minus what's restricting the motion, tension 1, Ft1. Okay. We know the mass of each block is 2 kilograms, right? Sorry, I'm zooming in and out. Mass of each block, 2 kilograms. The acceleration of the blocks we found in part B was 4 meters per second. Okay, force of gravity, right? mg, so 2 times 10, and then minus Ft1. Okay, so we get this 8 is equal to, nope, not that. 8 is equal to 20 minus Ft1. So this would mean Ft1, right? Add Ft1 over, and then we can subtract 8 equals 12. It's a force, so newtons. Okay, Ft1 equals 12 newtons. Nice. Okay. Our next part D, says find the tension of Ft2. Find the tension of Ft2. I'm going to take this diagram and move it out of the way just a little bit. I'd say for part C, look at there. Tension for Ft2, well, look at all the places where Ft2 applies. It happens on the pulley, right? Ft2 creates this torque from tension 2 because it's an off center. The other place this happens is on the block. Ft2 helps pull the block forward. The problem is we don't know anything about the other part of this block. We don't know friction, right? Because friction, mu, Fn, well, we know Fn, right? Because this is sitting on a table, so normal force must be equal to gravity, but we don't know mu, right? We really just don't know mu in this situation. So we cannot use that approach. We can't look at that block, which means we have to look at the pulley. Remember, the pulley has this torque of tension 1 being applied to it right there. All right. So we have to look at it through the lens of the pulley, so let's do that. Well, we can't say forces, right? Because they're not acting on the center. So what do we have to say? Some of the torques. And I'll just say it doesn't even need anything because we only have one rotating thing. Some of the torques on the pulley. Okay. Some of the torques, we will do the exact same thing, right? I alpha equals, and this is exactly what you see above, right? Some of the forces equals ma equals all these other things down here. Some of the torques equals I alpha equals, then we have to do torques positive minus negative. Well, we'll do the same thing as far as which way does it rotate? That will be positive. So it rotates this way. We will call that positive. I know that's opposite from what we said earlier of clockwise versus counterclockwise. That was just to designate which way it rotated initially. But now, once we've passed that step, we can kind of just say, oh, which way is easiest to work with? Let's do that. All right, so this means that the torque caused by tension 1 is positive, and then negative would be the torque caused by tension 2. Okay. Let's start looking at some of these. Well, I alpha, we're given alpha, so I'll just hang on to them for now because tension 1, right, is R1 F T1 sine of that theta minus for tension 2, R2 F T2 sine of whatever that theta is. But let's look at these. All right, well, if we take these tensions here, let's look at the radii that we have first. Let's try to figure out the angle. So, right there's the radius. There's the radius. For this tension 1, there's the radius. Well, if that's our radius, goes from left to right. This is our force, goes straight down. What's the angle between those? 90 degrees. Okay, so that makes our life pretty easy because that means the sine of theta for this tension 1 is 90 degrees. So that sine theta, sine of 90 degrees equals 1, so that just goes away. How about for the other one? Well, we have radius vector goes up from the center to the point of contact, and then the force comes out from the point of contact out. So if we look at that, we get another 90-degree angle. And sine of 90 degrees equals 1. So what will this sine of theta turn into? Turns into 1. Okay. So what this truly means is now we have I alpha is the radius, and this is actually, I should say, this is the radius of the wheel times force of tension 1 minus the radius of the wheel again, right? That's the distance between the center and where it makes contact. For both of them, it's just the radius of the wheel. And then force of tension 2, we got rid of all the sine thetas. Okay, so now we can plug some stuff in. Well, I have to look up higher up the page. We get 0.03. Alpha, we had as 20. All right, so 0.03, and that's kilogram meter squared. Alpha we had was 20 equals, okay, radius. Radius we have 0.2. Okay, 0.2. That radius was times ft1. All right, that was from the part right above, so 12. Minus, again, the radius, 0.2, times this one ft2, and that's what we're solving for. All right, so if we plug all this into a calculator, all right, we get 0.6 is equal to 0.2 times 12 gives us 2.4 minus 0.2 times the force of tension 2. All right, and then I trust that, or at least I hope that you all by this point in time can take all of these equations and do what you need to solve for them. We get Ft2 9 newtons. Okay, so there's our force of tension 2. All right, if you need to go back and pause and rewatch any of this, please do so now. I'm going to keep going. 2 parts left. E, determine the force of friction between the table and mass 2. All right, well, what's the only thing the force of friction applies to? Mass 2. That's it. All right, because we have force of friction holds it back, but we have force of tension 2 keeps it forward. There's gravity and there's normal force, but those cancel out. Those are not in the direction of motion, which means we don't really have to consider them for right now, at least. So if force of friction only applies to mass 2, that means we have to look at mass 2. And mass 2 doesn't rotate, so it's not torques, which means what do we look at? Sum of the forces equals MA equals, all right, positive forces are where it goes, negative forces are the ones restraining it, so FT2 minus force of friction. Mass, we had masses were 2, I believe. Yes, masses were 2. Acceleration, we had that was 4 equals FT2. That's what we just solved for. 9 newtons minus force of friction. All right, solve for force of friction in this. I believe you should get 1 newton. All right, and there's your force of friction. Okay. Finally, part F, coefficient of friction. I hope you're good at this by now. Force of friction equals mu Fn. Yes, mu Fn. In this case, because, I'll call your attention to the left side again, because normal force has to be equal to gravity, that's how we know that Fn is equal to mg. It is not always the case, but because those are opposite, there aren't any other forces, then they have to be equal, which means, okay, let's plug this all in. 1 is equal to mu, mass is 2, g is 10. So if we get mu is equal to 1 over 20, mu gives us 0.05. Okay, I'll take a look at that. We just did our first problem. This is a hard problem. This is a really hard problem. This page 20 and 22 that I'm cutting out, at least at the time I'm taping or making this video, the pages that are getting cut out are harder problems than this, which is why we're cutting them out. It's why you're just don't worry about them. All right, process for this. Always look at 1. If I'm asked for a force or for a torque or a tension, whatever it is, what does that apply to? What object does it apply to? 2, do I have enough information to set up an equation for that object? And 3, then you plug it into the equation for either some of the torques or some of the forces and solve for the rest of it. All right, let's go to our next problem now. So this is the setup for our problem here. We've got a mass that unwraps. Find the acceleration of the block as part A. All right, but we've got an 8 kilogram mass. 8 kilogram mass unwraps a rope that's been wrapped around a pulley. Mass of M, radius R, uniform disc. Okay, mass is 4 kilograms. Kilograms got kicked to the next line. And radius is 30 centimeters. Determine the following. Acceleration of the block. Okay, so we need to find acceleration of the block. A equals question mark. Well, there's a couple ways we could do that. Right, what are the ways we know how to solve for acceleration? We've got motion equations. And right, these would be linear motion equations because it's linear acceleration. We know A is equal to alpha R. And we've got sum of the forces equals MA is whatever forces are there. Okay, so if we're trying to find acceleration, well, what are we going to look at here? That's a great question. We can, right, if we're looking at sum of the forces equals MA, we would need to know gravity right? Because this is, I'll erase these dots actually, because this would be gravity is helping the motion and tension is hurting the motion. Helping is, or tension is holding us back. Well, we don't know tension and we don't know A, so we can't use this approach. Okay, how about A is equal to alpha R? Well, we don't know alpha and we don't know A, so that's going to be really hard too. Okay, so we can't really use that too much. Motion equations, do we know anything about time or distance or velocities? Well, we really don't know any of those. We would need three of them. All right, where does that leave us? That actually, it leaves us with solve for alpha first, because we do know the radius. Solve for alpha, then we can get acceleration. If you solve for alpha, you can get acceleration, which means, yes, we have alpha as a question mark, or A has a question mark, but what we first need to do is solve for alpha. Okay. First, we need to solve for this alpha here. Well, how do we solve for alpha? Rotational motion equations or sum of the torques? We don't have enough for rotational motion equations, which means we are stuck with sum of the torques equals I alpha equals. All right. Well, what thing could we possibly be looking at torque for? Well, if it has torque, that means it's rotating. So this means we're doing sum of the torques on the disk. Okay, well, if we take a zoomed in look at our disk, all right, we have tension is being exerted here, so force of tension, which creates this torque of tension, and that's at the full radius r away. Do we have any other torques? Well, nothing's acting on the wheel, and it doesn't tell us about friction, so I don't think we have any other torques. So this means that our sum of the torques, all it is just going to be our torque of tension. All right, so if we zoom in, we can get I alpha. Alpha is equal to, right, R F tension times sine of theta. But this sine of theta, I'm going to slide over. This sine of theta is just like before, where our radius vector and our tension force are perpendicular to each other. And sine of 90 degrees is 1. So that sine of theta goes away. All right. Now we need to know I in order to find alpha. Alpha is what we're looking for. Okay. Well, this is kind of difficult because we don't know tension either. We'll get there. We'll get there. This is a convoluted problem, so just don't worry about it so far. Basically, right? We have a disk. We've got this uniform disk. If you look this up, I for a disk is equal to 1/2 mr squared. On any sort of AP test, they'd have to give it to you. All right, so we have 1/2 times the mass times the radius squared. This is times alpha is equal to the radius force of tension. Well, we can cancel one of these radii with the squared function. Well, actually, oh, didn't mean to do that. R squared, cancel out with the squared. We can cancel with this radius. So we really get this 1/2 mass radius alpha equals force of tension. But we don't really know force of tension, do we? We don't know that yet, but where does force of tension appear? It appears on the wheel and it appears on the block. So if we can't get this all the way through the wheel, let's try this with the block. Let's try, that pen's a little thin. Let's try this one here. Let's try this sum of the forces on our block equals MA. That's on the block equals MA. Well, the block's moving straight down. What's helping the block move? Force of gravity. What's hurting the block? Force of tension. So we have gravity minus force of tension. Okay, we know the mass of the block. We're trying to find the acceleration. We know force of gravity. We don't know force of tension. Okay, so unknown, unknown. Back to the torque situation, unknown, unknown. Hmm. We can almost set up a system of equations, except for we have alpha and we have, sorry, alpha over here and we have A over here. Well, if only there was a way for us to relate those two. Oh, wait, there is, right? A is equal to alpha R. Wow, that was not how I meant to write that. Is equal to A is equal to alpha R. And since we're solving for acceleration, let's plug in for alpha so we can substitute alpha out. A over R. Okay, so let's try this. 1/2 m r. A over R is our alpha now, is equal to force of tension. All right, well, we got radius, radius. Those cancel out. Nice. So really all this is, we have force of tension is equal to A times 1/2 mass. And this is mass of the disk, right? This mass of the disk, because this comes from the torque acting on the disk. Okay, so now we have two equations, two unknowns. I'm going to unhighlight the ones over here so we don't think we have to use alpha. But we have two equations and two unknowns, force of tension and A, acceleration. As a pause moment, this problem is much harder than anything you would see on an AP test. They would give you acceleration, or they'd give you a way to find the acceleration first, and then you could just plug it in. Maybe they would ask find force of tension. But because of the way this problem is set up, with what it gives you and what it doesn't, it requires you to go through both some of the torques and some of the forces, and that is an experience I don't want you to miss out on. Okay, so we're down to these two equations, two unknowns, but we haven't really gotten this forces equation down as well as we could yet. So let's take this mass. This is the mass of the block, because these are the forces acting on the block, times acceleration of the block is equal to mass of the block G minus force of tension. Okay, why not plug in some numbers? Mass of the block was 8. Okay, so we can get 8A is equal to, 8 times 10, or 80, minus force of tension. So this tells us our force of tension is equal to 80 minus 8A. If you need to pause and think about that algebra for a moment, go for it. Okay. We can plug in over here a little bit too, right? We have 1/2 time. Oh, I'll use back to the color I've been using. 1/2 mass of the disk. What did I say that was? Mass of the disk, I said, was 4 kilograms. Was 4 kilograms times A is what we don't know, is equal to force of tension. All right. Right, but that's 2A is equal to force of tension. Well, over here, I have force of tension equals 2A. I have force of tension equals 80 minus 8A. Huh. Weird. It's almost like we can just set those equal to each other. Let's do that. Because if this equals force of tension and if this equals force of tension, they have to equal each other. So 2A equals 80 minus 8A. All right, we'll add 8A to both sides. Okay, so we get 10A is equal to 80. Nice. Our acceleration equals 8 meters per second squared. Look at that. Okay, complicated portion of the problem. Right? We had to think through what could we use and how could we get there. And then when we ran into a situation where, oh, we have two unknowns, how can we get those still? Well, we come up with another equation. We have two equations, two unknowns. This is a hard problem. I will never expect you to be able to do something like this on your own, at least not without the guide of this these class notes in front of you and what you've been working with here. Your homework does have a question almost exactly like this, but it's almost exactly like this. So you can use this problem as a guide as you work through it. All right, part B, angular acceleration of the pulley. Well, if we take angular acceleration of the pulley, right, that is alpha is what we're looking for. I'll take a look at this. We already set up an equation for it. Alpha is equal to A over R. We have our acceleration is 8. We have the radius of the pulley is 30 centimeters, so 0.3. So if we set this up and solve for it, 8 over 0.3 gives me 26.7 radians per second squared. There's our alpha. Well, one thing that is kind of fun, you might notice, sorry, just backing up. I saw this 0.3. I was like, oh, we haven't used that yet. So the radius actually didn't matter whatsoever in this block, falling down. Well, if you remember back to a similar problem that we did when using rotational energy, that's what we found also, is that radius did not matter. Radius just didn't matter, which is kind of cool. Okay. Last part, part C, what's the tension in the rope? Well, I'm going to use this right here. All right, force of tension, I gave you a really easy expression for it. Force of tension is equal to 2A, and by I gave you, I mean, we found one, we derived one. It's equal to 2A, which would be 16. Oh, this is a force, actually. I was about to say meters per second, but this is a force, which tells us that it is meters per second. No, wow. My apologies. This is a force. It is newtons. The force of this would be 16 newtons. Okay. That's it. There you go. You have now gone through two of pretty much the hardest problems we could go through. Aren't you glad we didn't do the other two? All right. Well, I hope that gives you a good starting place so you can answer the questions on your homework. They are exactly like these two, just slightly different numbers, but the exact same situation, slightly different numbers. If you have any questions, please do let me know. But otherwise, have a great rest of your day.